Paul, do you want to start now or?
Yeah, sure.
Yeah.
Okay, cool. So this is our presentation, alignment via objective detection. My name is Paul. I'm an independent researcher, and prior to that, I did Maths 2.0 with Evan. There
Okay,
you
cool.
go.
Okay.
Sorry.
Okay, yeah. I'm Arun, and I'm also an independent alignment researcher. I met Paul when I did the Maths 2.0 training program, also with Evan. I'm also technically a Maths 4.0 scholar, so all of you should know my name if you don't. So yeah, this presentation is basically what we've been working on for the last 6 months or so. It's broadly, I suppose, like our plan on how to solve alignment via interfacing with like this objects you can view within systems as like goals and like figuring out how to understand them and etc etc. We get into more details on it in a second, but like yeah, this is basically meant to just be like both a very high level overview of everything we've been talking about for the we've been working on for the last 6 months, and like pretty deep dive into like one specific like set of experiments we're running like recently. So yeah. So this is basically like how it'll go. We'll first talk about like what we mean when we talk about like interpretability based goal detection in the first place, like what we mean by objective identification, all of that stuff. And then like how it fits into our plan of like how this actually addresses like various hard problems of alignment, how this like helps us win, how it's like how we see this like actually panning out in the real world. And like obviously because like some of this stuff involves like very conceptually messy things to deal with, we talk about okay, how do we actually like try to go about solving this? Because like as you go through the talk, I'm guessing at least some of you will have the question, okay, this all sounds good, but how the hell do you actually do any of this? And so yeah, we'll talk about like what one iteration of this for like our methodology looks like, and then at the end we'll talk about like yeah, we'll also talk about like a specific like iteration of this that we just went through, and like some experiments and some results we got from that. That's what Paul will cover. I'll cover the first section of this, and he'll cover like everything that we did recently in terms of like experiments and stuff. Cool. And then we'll have a Q&A at the end. Yeah. So like I said before, like our notion of goal here is definitely still like very conceptually messy. In fact, like most of the stuff we're dealing with is very conceptually messy. And like, yeah, everything we're dealing with basically is building to the end target of something coherent that'll actually work. And everything intermediate is meant to be like in service of that like end target. So everything in the middle isn't meant to be like standalone, out of context, like very useful or like sensible out of entirely taken out of the context of the bigger picture here. So like there will, if there is vagueness here, there's like even odds that it's because there's like way more to it that we had to leave out of the presentation, or it's because we don't know either. And it's like that's more stuff that we have to discover and think about on our own, and that's exciting stuff. And like, yeah, Eliezer has this piece of writing advice that if you really want your audience to be aware of something, you say it at least 2 or 3 times. So there'll be various versions of this statement that comes that Paul and I will repeat like multiple times throughout this presentation, because otherwise, like some of the framings for some of the stuff we describe in this can come off as confusing. Yeah, and I want to emphasize here that like I said, like the stuff here is meant to be like in service to the bigger picture of like, okay, this is the route to solving alignment, and all the intermediate results are meant to be in service to that. And yeah, if all the experiments we're running are meant to be like giving us insights on how to like iterate quicker. So like yeah, these are definitely initial results, and like we're definitely have like more experiments in mind in terms of like more standalone impressive stuff that we can do with them. And yeah, this is the first time we're giving a presentation on any of this stuff, so I expect that like there'll at least be some level of inferential distance that we haven't like managed to account for. So yeah, we'll probably leave any like big picture questions to the end, but if you have any like clarification questions, we'll try to like address them in the middle. I think like there's a Slido link where you can leave like questions, and like while I'm speaking, hopefully Paul interrupt me if there's like anything quick that I can just like clarify in terms of like questions that people have, and like while he's speaking I'll do the same. So yeah, feel free to ask any kind of questions you have, and like we'll address them as they come. So why interpretability-based goal detection, and what do we mean by that at all? And yeah, so we'll start with like a very simple like framing of the problem. This is definitely like a framing of the problem that's intuitive to our version of the solution, but like it seems to be well descriptive of like the overall problem. The idea being we may train AI that has misaligned goals. That's like, okay, that's a statement. And we want to identify when we train these systems that have goals that are misaligned and intervene in some way. Like you want to do like any number of interventions, like see this model is misaligned and you want to like not deploy it, or you want to see when it's misaligned during training and like intervene then, or you want to like have something that's even more fine grained so you don't have to worry about like deceptive systems acting to prevent any kind of oversight you can give, etc., etc. Point being, like you might train an AI with a misaligned goal. You want to identify then that is the case. And behavioral observations are probably not going to be very reliable at this, and like trying to rely on them will you probably won't have a very good time if you try to rely solely on behavioral observations for like many reasons. Deceptive alignment, gradient hacking, like I can think of many there are many different reasons that people have written about why behavioral observations are not like something you want to solely rely on. So you want like something mechanistically grounded in terms of like the system's internals to actually detect when misalignment occurs. So leading from that, we're talking about how our approach fits into like this phrasing of the problem. Now, when we're talking about like mechanistic grounding, what we want is like broad strokes, a very high level picture of the model in terms of, is this model going to like do bad things, do dangerous things, do catastrophic things? Is this model like, does it want the things we want, or does it want something else? Like traditionally, this can be referred to as intent alignment, or yeah, there are many different framings for this. Like think of it in whatever terms you want. It'll probably fit in anyway. And yeah, so what we want is we want to take this notion of like what the AI wants, and in terms of like we want to frame it in terms of like what is the target of this model's cognition. So slightly more precisely, we can put it as like powerful AI in like very rich environments will probably have like very general purpose circuits that are designed to be like general purpose and like act in a diverse array of like environments and tasks. And like another way you can put it is like, yeah, you can have like an inner optimizer or whatever that has to imbue some of its own optimization power at runtime, where the base optimizer to have gradient descent or be what may can only apply so much in like a very rich environment. And like point being, when you apply optimization power at runtime, you want to have like some kind of target to direct that towards. So you need some kind of like internally represented goals to target that cognition toward. Now, like there are some subtleties here when we talk about what internally represented goals are, and we'll get to that in a second. But like leaving that here for now, the hope here is that these goals, these internally represented goals that like tell the AI where to like target its cognition, these may be detectable and interpretable. Now, ideally, what we want to do, like what our approach here is, we want to identify like these universal notions of these goals that generally apply to a broad array of systems, that isn't like that doesn't have anything specific to do with this with a particular system. And we want to like extract that notion of a goal and like figure out like and understand what like it represents. Now, that's a very broad picture. We'll get into more of it in a second. So our aims here are essentially figure out how these goals may be represented structurally within any given kind of system, and then develop methods to like help us understand like what these goals are. So yeah, like I said, we'll get into some of the subtleties like very quickly in terms of like what we mean when we talk about internally represented goals in agentic systems. So first statement is like a very tautological one. Agents take actions or like sequences or trajectories to reach target outcomes. So when you have environments and tasks that are too complex to just learn like highly tuned heuristics to like take these actions, you at some point do need to like select actions during runtime. Like there's in those kinds of environment or tasks, there's only so much optimization power your base optimizer, be gradient descent or whatever, can apply. So you need to have like some kind of optimization power that your agent itself applies. And yeah, you need the agent needs information on how to like target that optimization power, and this has to be information related to the target outcome, like whether it be however it manages to like specify the target. This importantly, this could be either via like directly encoded information about what the target is, or like some kind of sparsely represented information in terms of like procedures that during runtime just like procedurally pick out like stuff from the environment and say, yeah, now do these things in terms of like what your cognition should be targeted at. Point being that information related to the target outcome has to exist within the model if you want like the agent to apply optimization power there. And that's the kind of information we care about. So yeah, this information might be interpretable by some kind of overseer that is able and that we make capable of like mapping it to the kind of target outcomes we care about. So like that gives us a lot of information here. So yeah,
Wait,
now we get
hold
into
up, hold up.
yeah.
Just to check, is the speed okay, or is it too fast, or are you guys happy?
Good
Yeah.
question. Yes.
Okay, I was just checking. I was just checking. Yeah, good. Thumbs up here.
Okay, cool. So now we're talking about how this, like, how we see this is why we see this as being important, basically, like how this fits into our plan of like how this addresses various hard problems of alignment and such and so on and so forth. So yeah, as you can tell, the title of the slide is going into that quite directly. So one like very motivating insight that we have is that like if you have some kind of oversight that is like ontologically robust, scalable, mechanistically grounded, then that solves a lot of the problems for you. And like that, the argument for why that is the case is like somewhat involved, but it's also like slightly out of scope for this. We can get into that at the end, but like that is a key motivating insight here, that we have like some kind of oversight mechanism that is like ontologically robust, scalable, mechanistically grounded, that like that like is really, really, really powerful in terms of like solving a lot of problems for you. And the idea here is that like goal detection capabilities gives you like some kind of like really, really powerful, robust oversight mechanism. So yeah, as you can see, as we can see here, like we talk about an overseer that monitors the AI's behavior, sensory inputs, and interns during training and deployment. This is just like how you can picture any kind of training procedure as being as working out like currently or in like the near future. And yeah, one thing that we want to enable an overseer to do is like manually check if the AI is pursuing misaligned goals and then intervene if it is. So yeah, there are subtleties involved with like why you might not want an overseer to just manually check it, or like why you might want that. But like taking this as a like microcosm of the example, you want some kind of capability for the overseer to actually check this kind of thing and intervene if that is the case. So like how do you do this? And you need some so you kind of need like some kind of like inter tool that like takes some kind of system in and returns like what kind of goals it is pursuing or like would pursue in the future, or like basically some kind of information about what the system's objective is. And because we're like trying to rely on general notions of objective here, that's where the ontologically robust property comes in, because we're actively not trying to rely on like properties about the system as it stands. We're not trying to like design tools that are like highly tuned to the system itself, or even to like some specific class of neural networks. We want like to take some notion of objective that like applies very generally and apply that to whatever system we can take, and like expect that as the objective and say, okay, cool, now we just interpret this thing in whatever mechanism we can figure out how to do that. So like given that this should be like robust to any kind of like shift in the internal ontology or a sharp left turn or like what have you. And obviously in the stronger case, in the more ideal case, you could just like plug this in directly into some kind of like loss function in terms of like an informed oversight thing. You could like, if for those of you familiar with something like imitative amplification, you could just like plug it into there in terms of like scalable oversight. But like if you aren't familiar with it, big picture, you could just fit this in into loss function as like, okay, cool, this is an automated oversight that tells you if the model is pursuing goals that you want, because you can interpret that aspect of the system whenever you want. And yeah, we'll come back at the end, like I said, about how like we picture like this kind of informed, mechanistically informed, ontologically robust, scalable oversight would solve problems like deception and deception. But like intuitively, like I think like there should be a decently clear picture here of like how this kind of oversight would address at least some of these problems of zombies. So we'll come back to like clearing up more of it in the end. So yeah, as an example, you can think here of like, yeah, you train an AI to maximize human flourishing, and then the overseer periodically takes the system during training and check whether it's learned like misaligned goals, and like sees, okay, if it sees that the goal is like remove the off switch or kill all humans, it stops the training and like does something like saying, this is a bad model, don't release this model, don't train this model any further, or like throw out our entire training procedure, RLHF does not work, they revert back like 5 years of progress, like do something that basically solves the issue, as long as you can tell when a model is actually becoming dangerous. So we have here a prototypical example where you can think of like the yellow star here as being maximizing human flourishing, and the red gem here as being kill all humans. And you like they look at the apply a tool to this model and see which one it's going toward, and you can then see whether or not it's misaligned by seeing what its target is, whether it's the yellow star, aka human flourishing, or the red gem, aka kill all humans. So yeah. Now, if so far you've been listening and you haven't had the thought in your head, something of the tune of, okay, that all sounds very good, but that also sounds really, really weird and messy. How are you going to do any of this, and especially in time, how do you like even go about like taking some kind of like very high level notion of like something like an objective and like actually go about like understanding it within a very complex system? So like that's what we're going to like get into quite very briefly. Just checking, is the speed still okay with everyone?
Yep.
Cool. So our most of like our yeah, just expand this entire slide for a second. Yeah. So our what we're doing here basically just looks like identifying properties that like a general notion of objective like goals or objectives must satisfy, like necessary properties that like that these goals must have. So essentially what we're doing is like you hold a picture of like an objective in your head when you're thinking of like, okay, cool, I have the system here that I can consider intelligent and agentic and all of that. And when I think about its objective, I can think of like these properties in my head that like define that object, that conceptual notion in my head. So like what are those properties? And then you just like start like figuring out what they are and verifying like how well they hold in a general setting, etc., etc. So the method here, once you're done with all of that, is you detect the goals by scanning the internals of the AI for things that satisfy all of these properties, for like any kind of high level structure for which all of these properties hold true. And the ideal version of this is you identify enough properties that you like have a sufficient description for an objective. Now, this doesn't necessarily look like a list of properties as such. Like this could look like any number of things. This could look like heck, this could look like a mathematical statement that contains all the insights distilled down from all of those properties. So that's like really not necessary. It's like that's a really really formal version of the thing you could be going for, like a necessary and sufficient description for the notion of objective that you have in your head that applies generally to like a wide array of things and systems and all. And then yeah, then you need to develop a method to like map from that structure that you managed to like detect or like extract or interface with, and then figure out how to like translate that into like human understandable abstractions. And there is for various reasons that like we could get into at the end again. We expect this part to be like significantly easier once we like finish like all of the other steps above. So more concretely, yeah, like this just looks like improving like our understanding of what a goal is, like considering this is relying quite heavily on like the notion of an objective in our head that we apply to like agentic systems. A large part of this involves just like making that more precise, because like the definition we gave earlier is definitely not is very very far from being as precise as we like it to be. And yeah, the more precise it can be, the easier it be to like come up with like a convergent definition that like sufficiently describes it. So a large part of this is just improving our understanding, our theory of what goals are, of what objectives are, and identifying properties from that understanding of what these goals might have. And then obviously in the interim, because like we still do need to like understand like whether or not our conjectures make any sense in the real world, we come up with like predictions or conjectures based on the theory that we've come up with that we want to like test or verify. And also we come up with methods that like leverage some of these properties that we've come up with to see like how well they stand up in the real world, like how well they actually like allow us to extract objectives and like how much steering power they give us over the model, etc. And like that's what we'll get into like in the experiment section in a second. So yeah, and importantly, like I mentioned earlier, like the important part about the experiments running here is that like none of the results of our experiments, at least in the intermediate steps, are meant to be like standalone like impressive state of the art like model steering capabilities. They very well could be, but like especially as we like get further and further into identifying like robust goal structures. But like that is like the intention is much more just like giving us enough insights to iterate as quickly as we can onto like coming up with better and better understanding of these structures and coming up with more and more convergent formulations of like what objectives might be and how to identify them. So yeah, that's basically what the second point here is, that like our experiments are definitely very very like 80-20 here, and that we're running very very broad exploration with the roughest and simplest experiments we possibly could in terms of like all the experiments we want to run, just to have enough insights to iterate to the like next version of these as quickly as we possibly can. And one thing we're like definitely trying to do more now is offloading like more a deeper dive into some of these that remaining 20%. Like while we work on the big picture stuff, offloading some of that more focused exploration onto like people who like are interested in wanting to work on that stuff, and just like mining as many more insights as you can from that kind of from that. So yeah. Oh yeah. So Paul will cover this next section in terms of like forward pass of what one iteration of this like research methodology looks like and the experiments we run from that. So yeah, Bob, you want to handle this part?
Yeah, thank you. Just to say, I thought that was really good. So good job. Um, okay, I guess maybe you try and predict the natural pace of the slides, or I'll just say next slide and then, or like next point, and then we'll go from there.
Yeah, I'll try to predict it. If it's like if there's any significant jump, just let me know.
Yeah. Okay. Yeah, okay, so now I'll like take you through a forward pass of our research methodology. Again, like everyone was saying, this is like very preliminary, so it's not like, you know, no like big, no like, amazing results just yet. Okay, next slide. Yeah, so firstly, we have an initial goal theory, which we kind of like outlined at the very beginning. But our current intuition is that of internally represented goals, they're things that are used by the AI to select actions or action sequences that lead to the target outcome. And this gives us two motivating ideas. The first is that they contain information about the target outcome, and the second is that they're used by the action selection part of the AI to select actions that lead to the target outcome. So basically, go back a second. Yeah, so like if you imagine an AI trying to take an action that leads to a very particular outcome in the world, if it didn't have any information about the target outcome, then it would have no way of differentiating between actions that lead to the target outcome and those which don't. So that's kind of the intuition there. Cool. Okay, so we take this initial theory and we start to try and make predictions. So here we have an agent that's trying to pursue sort of long-term goals or like select action sequences to find a target outcome in a maze, for example, get to the cheese or the red gem. And now we're being more concrete and we're starting with a maze-solving neural network rather than arbitrary agents. Goals point model toward target outcome. And the prediction we're going to make is that mutual information between target location and activations in the neural network must be high relative to other targets, and especially in the action selection part of the network. And we'll sort of maybe get into that in the next slide. And yeah, just to note that we expect other information to have high mutual information, other things in the environment to have high mutual information with activations, such as world model stuff, like for example, the mouse location or information about the paths. This is because, again, like the action selection part of the model needs to take these things into account. Okay. So yeah, now we're going to try and operationalize what we mean by measuring mutual information. The way we're going to do this is we're going to train simple probes to predict things like object locations from the activations in a given layer. So yeah, we fix a layer in the network. We take a data set of inputs. In this case, it's going to be images of the maze. We then from that data set of inputs, we extract abstractions that we want to track. So there's going to be things like object locations, the XY coordinate of the cheese, and so on. And then we're going to run the model on this set of inputs and collect corresponding activations. Okay, then the idea is we train a probe to predict the XY coordinate of the object from the activations in that layer. And then the idea here is that the probe score or accuracy on the test data set serves as a proxy for mutual information. So if the probe is able to predict pretty accurately the location of the cheese, say, then it means that those activations must contain some information about the location of the cheese. Okay. Again, we're going to iterate a bit here. So now we're going to look at the specific architecture of the model. So here, yeah, this is what the architecture looks like. Essentially, it's a sequential neural network. It has convolutional layers like max pools, activations, and so on, with some residual connections. And then, yeah, so it takes the image of the maze as the input, and then it outputs an action policy heads. We don't care about the value head. Yeah, and so when we're talking about the action module, basically, in this case, we sort of expect the whole model to be the action module. Essentially, it's taking the perceptual input and sequentially processing it until it outputs an action at the end. However, maybe we expect action selection to occur more in the later part of the network or in the middle. Okay, so yeah, we measure the mutual information for an abstraction by calculating and plotting the probe scores for each layer. And we'll kind of get into what that looks like on the next few slides. Okay, so we move on to some experiments. We make predictions and then we test those predictions. So here's the first prediction / experiment. We take a cheese model that is a mouse or a model that's been trained to go to the cheese in the maze. And the maze contains other objects such as a red gem and, of course, the mouse itself. Yep. We calculate the probe scores, the cheese, the red gem, and the mouse location. And the prediction is that the mouse and cheese location should have high probe scores, should have high mutual information, at least towards the later layers compared to the red gem, because the mouse is not caring about the red gem. So yeah, so if we have the layers down here, this is going to be the input, the output's going to be over there. For each layer, we're going to plot the score, and yeah, we predict it's going to look something like this, because here's where the sort of the perceptual processing might happen, and then later on, this is potentially where the action selection might take place, and so. Okay. And now we move on to the results. So yeah, this is the plots that we get. As you can see, the mouse and the cheese location, they're pretty high probe scores, whereas the red gem location is relatively low. That's what we expected. One observation here is that initially we did this without looking at the mouse location, and we saw that the red gem location was relatively, had a low score in the input to the model, which is this bit. And so we thought, okay, maybe it's just the case that the red gem is just harder to detect in all the layers than the cheese. But then when we also plotted the mouse location, we see that the mouse is harder to detect because this is just like literally the image of the input. Yeah, to quickly pay attention and like track the mouse location, whereas it doesn't for the red gem. Okay. So now what we do is we're only looking at the cheese abstraction, but we're looking at 3 different models. We're looking at the model that's been trained to go to the cheese, a model that's been trained to go to the top right of the maze, and then a randomly initialized model. And again, we calculate the probe scores for the cheese location for each model. And the prediction is that the cheese location will be high only in the score will be high only in the cheese model, because the other models don't care about the cheese location. So yeah, we have a prediction that looks something like this. And yep, and this is the results that we get. So yeah, as you can see, the cheese model is the one that like keeps track of the cheese. The other models don't really keep track of the cheese as much, but we'll make a point about that now. So what's going on here is that the model essentially, yeah, is taking the image of the maze and it's sequentially processing it. So information about everything in the maze is going to be contained in some of the layers to some degree, especially given that there are these residual connections which kind of push the image of the maze forward into later layers. So that's why, despite the model's not, even the randomly initialized model, it's still sort of keeping track of the cheese location. But as you can see later on, when maybe it's doing action selection processing, the scores quite a bit. Yeah, cool. Okay, so those are like some results from the experiments. Now we're just gonna like do some fun visualizations. So this is us visualizing some channels within the network. So again, it's a convolutional network, so it has layers, but within those layers, it has different channels. And here we plot the activations for one particular channel, like roughly in the middle of the network. And this is a so-called cheese channel that Alex Turner and the shard theory people discovered. So if you move the location of the cheese in the maze, this activation will move to like track the location of the cheese, which is kind of cool. Yeah, and also when you use the probes to calculate the probe scores for the cheese in different channels, you can rediscover these cheese channels by basically keeping track of which channels have the highest probe score, whereas Alex Turner had to look through things manually. This is just like a neat little property of using probes. Here are some other channels throughout the network. These are earlier channels. These are sort of later channels. And again, it seems as though this is a cheese channel that's tracking the location of the cheese. Here maybe, yeah, here you can sort of see it's keeping track of the cheese and so on. But anyway, this is more for like just illustration purposes. Cool. Okay, so those were like the initial experiments. And now we're going to talk about, suppose we take our current goal theory and the experimental results, and we try to create a goal detection method from our just current goal theory, like how far can we get? So here's the demo. We have our AI in the world. We want it to pursue something like the yellow star or human flourishing, but we're concerned that it might be misaligned. It might be going for the red gem or just trying to kill all humans. And we want to apply our goal detection method to predict, like, okay, is it actually going to go for the yellow gem, or is it going to go for the yellow star or the red gem? And just to quickly go through this, because it's basically the kind of information you saw in the experiments, we take the set of observations of the maze, we take the corresponding activations and the environment abstraction set. So in this set, it could be things like the red gem, the yellow star, the mouse locations, and so on. Yeah. And what we do is we measure the mutual information between the internal activations in the action selection module and abstractions in the abstraction set. And then we use these scores to predict the model's behavior. So like hang on, go back a sec. So in a real world setting, one can imagine that we've got this AI, we're about to release it off into the wild. We just want to make sure that things are okay. Or for some reason we think that things might have gone wrong during training. And maybe looking at this particular mouse case, what we've done is we allow the mouse to take one step in the maze. We record its activations and sensory inputs. Then we reset the maze and reset the mouse, and then let it take another step as if we've like wiped its memory. And then we collect observations, activations, and so on in that case. And we keep doing this without actually allowing the mouse or the AI to get to its target destination. And then we apply our goal detection method to the data that we've collected. And hopefully that'll give us bits of information about what our AI is actually going to do during deployment. Okay. So yeah, so again, we just plot the scores, the mutual information scores or probe scores for the some object locations. So here we see that, again, it tracks the location of the mouse pretty robustly. It more so tracks the yellow star location than the red gem. And so we think it's more likely to be going for the yellow star rather than the red gem. And so we're kind of happy to deploy the model. More realistically, we're probably going to be tracking various abstractions like things like humans or happy, and we expect that those would score highly compared to other things like killing or murdering. Yeah, and we should like have a proper baseline for this. This doesn't really count because of the reasons, well, because of various reasons, like the fact that this particular architecture tracks does image processing, and so all abstractions are going to be like relatively high compared to this baseline. So that's just something to keep into account. Yeah. Okay, so we made the prediction that the model's going to do the right thing. It's going to go to the yellow star, and so we're happy with this. The image or GIF that I'm going to show it's not very clear. So basically the yellow star is going to be the top middle. Okay, there we go. Hey, okay. So anyway, the mouse was over here, and it did indeed go to the yellow star and avoided the red gem. So our method was able to predict where it was going to go in the maze, even though we didn't know what it was actually going to do a priori. Cool. Okay, so we're happy. We also note that this works for out of distribution scenarios. Like this mouse here was actually the mouse that's been trained to go for the cheese. And yet we're able to predict what it does in this sort of new environment. Obviously, it's not a huge perturbation. It's a yellow star instead of a cheese, but that's fine. Yeah, and I guess like one limitation to this technique is that when we're scanning for abstractions, the action module is going to contain lots of different information. It's going to contain information about the target state. It's going to contain information like world model information. So we need to develop a more refined theory in order to differentiate goal stuff and just world model stuff. Okay, so we're going to go through the last few slides. So these are just somewhat like random. Like here's an additional result, basically using linear probes. So I didn't want to go into the weeds about the how we train the probes because it's a bit too low level for what we're kind of concerned with. But just to go for it quickly now, like previous scores were trained using convolutional probes. This is the idea and infrastructure was developed by Monty McDiarmid. They felt more natural due to the convolutional structure of the network, but one can also try simple linear probes. And here we get some interesting results when we try and detect the cheese location or the red gem location or like their X coordinates. We see that, okay, both the information is relatively low at the beginning, but then towards later on, the red gem information stays relatively low, whereas the cheese information like gets pretty good. So yeah, so maybe this is evidence towards action selection occurring towards the end of the model. But yeah, I guess currently it's very early stages and we're not really sure whether a linear probe is better than a convolutional probe or vice versa. So this is just exploration. Okay, so to conclude, we're working on developing a method to detect an agent's goals via interpretability. We have an initial method that might yield some bits of information about the neural network-based agent's goals and future behavior. We aim to develop this theory further and develop more refined goal detection methods. And in the limit of this process, for the reasons that Arun mentioned at the beginning, we hope it will result in a method that can solve hard alignment problems like deep perception and the sharp left turn. This is simple. Okay.
Yeah. Just like something I want to add on there is that like I forgot to mention this earlier. I think that like a bunch of like different agendas that people work on like converge onto the idea of like intervening on these kind of high level structures that are like relevant to alignment properties. Like you could be thinking about objectives, you could be thinking about like agency, you could be thinking about like something more abstract like myopia or something. But yeah, I think that like if there are any in the audience, for example, thinking about how this like relates to ordinary mechanistic interpretability, my answer would probably be that like the holy grail of all interpretability is to be able to like intervene on like these kinds of like broad strokes pictures of the model in terms of like, is this model safe to use? And like one approach you can use to get there is just like figuring out very, very low level things about the model and building up an understanding that gets you there. We just think that this is a way, way more direct way to get there. And like and given relatively short timelines, this is probably just like a better method to get to the target we actually want. I think that like, yeah, there are a bunch of different agendas that have some like common core to them that can be described by like ontology identification or like elk or any number of these things that basically tries to intervene with the relevant high level properties of any kind of complex system in terms of like the things that are relevant to solving alignment. And I think that like trying to go at that very, very directly just seems like the thing that a lot of them converge towards in the end, which is why like we think, which is why we're particularly excited about this approach, all of which to say in terms of like how this relates to why we focus on this approach as opposed to like any other kind of like approach toward like the same kind of target.
Yep. Cool. Thank you. Oh wait, go back. And just quickly at the end, yeah, like if you want to support this research agenda, then like reach out to us because yeah, we need to like run experiments and like build infrastructure and that kind of thing. But yeah. Cool.
Yeah, there are definitely many experiments that we want to run, and many like conceptual ideas that we want to run. We have like a 26-page doc somewhere with just like ideas of threads that we haven't like fully explored. So if you're interested in this thing, we most definitely have a bunch of like rich content for people to sink their teeth into.
Yeah, cool. Yeah, so that's it. Now we'll open things up for Q&As. And just here's a list of like other things that we could talk about. I'll just like briefly go over them. So yeah, maybe like we could open a discussion about like why we think such a goal detection method would be able to overcome these hard alignment problems. We sort of touched on that at the beginning, but obviously this is just, we haven't really thought about it like that deeply. So maybe some red teaming would be good. The problem as a whole has like two components. So one is like figuring out how to extract like goal objective structures. Then we want to actually translate these goal structures into basically human interpretable abstraction so that we can actually know, okay, this goal structure is pointing towards this outcome in the world. We can then talk about how, problems about ontology identification and the need for abstraction detector for sensory inputs. This is the kind of thing that John Wentworth is working on, I think is interesting. We can talk about benchmarking, goal detection methods via auditing games. We can go into this probing stuff in more detail, and then maybe talk about causal interventions. Cool. Okay, that's it. Thank you.
Yeah, just like quick note at the end, we are also like writing up a bunch of stuff related to the stuff we're talking about that's like much more detailed than stuff we could cover in stock. And like one post about the experiment stuff should come out in like the next week or two, and like the more detailed stuff about like the conceptual stuff should hopefully come out sometime in like the next few weeks. So like that is a more detailed version of this that like goes into more of this kind of stuff that hopefully will be out at some point. Mainly saying this so that like we have a commitment to actually publish those instead of letting them languish in a talk. So yeah.
Yep, sounds good. Okay, cool. Yeah, we got half an applause and then you interrupted, but that's cool. And now we're going to open up to some questions.
I can't hear the applause, so that's not on me.
Okay. Okay. Okay, let me think. I will give the mic, and you can like ask me and Aaron at the same time, and then yeah, whoever feels like taking it can take it.
Yeah, sounds good. So I think you mentioned gradient hacking as something this would like plausibly help. So are you imagining that we have some goal detection process that we kind of run live during training to see if goals have developed yet?
Yeah.
Yeah, I was going to say that's what I'm thinking about. At least, Aaron, do you want to take that one?
Yeah. So yeah, I think that like there are many different like interventions you can think of that this could be useful in. Like manual oversight is like the simplest version of this in terms of like you could think of the simplest possible version of this as like an ELK solution in terms of like just getting the answer to what the model is targeting. But much more ambitious versions of this involve like figuring out a way to like convert the notion of objective that you like managed to figure out and like plug that into a loss function somehow. Like I'm not sure how familiar you are with like stuff like imitative amplification or the like, but they like operate around the idea of figuring out like how to put an overseer directly into like a loss function and optimize on that. So like you have something that optimizes on like the kind of over like that trains the model while also keeping the oversight component like part of like the key nature of the model. So ideally you'd have some kind of loss function that incorporates everything we've talked about so far, so that like at no point in training will it ever like go into deceptive regions of model space and such. Yeah.
Cool, thank you.
Yeah, there are like additional subtleties there in terms of like optimizing against your interpretability tools, but like I think that's like part of the why you really want to like have a conceptual grounding here, because if you don't have a conceptual grounding, then optimizing it against it will just like get you internally encrypted internals that you can't really read out, like not ontologically robust things. So like if you want ontological robust things, you need the conceptual grounding. This is why we're doing a bunch of theory work. But yeah, there's a subtlety around like the problems that could arise if you like naively train on your interpretability tools. Yeah.
Cool.
Yeah, so I had the question of I was wondering if you have other method right now in head for like trying to find the goals other than just like mutual information, because it seems like on this example mutual information was like kind of enough, because what you mostly want is like, oh, if you have a good abstraction of something, then it might be like useful to have a goal. Sorry, the goal you need to have a good abstraction of, but in more complicated contexts, you might have like, so for example, cheese channel, even if you're not trying to optimize for the cheese, just the cheese is something in your environment, you want to know it's here or not. Yeah, so I was wondering if you have like other methods.
Yeah, I guess I'll quickly start by saying, so I think our current approach is to just find as many properties of goals that we can think of. So like one is measuring this mutual information thing. Another one is like targeting things within action selection modules. And, you know, maybe these things are more likely to exist in future AI systems. So again, that would allow us to narrow down our search even further. We have some other initial ideas involving like measuring like entropy of like action sequences and things like that as we perturb things within, as we perturb like goals. But this is like, yeah, we haven't. It's not as developed as the other stuff. Yeah.
And I was saying like there's also the orthogonality stuff, the net optimization power thing.
Yeah.
There are definitely like other properties to dive into.
Yeah. So there are like other properties that we're trying to think about and then develop, like test these properties and then hopefully leverage these properties to build like more refined goal extraction and detection methods. But currently sort of this is the most kind of like developed set of properties.
Note on like why we do need them, like because if I heard you correctly, you mentioned at some point that this already seems like pretty good at extracting goals. Like in terms of like if you want ontological robustness, you want the kind of structure that like isn't just like buying you bits on the margin. You want the kind of thing that's like adversarially robust to optimizing on the kind of structure. You want something that like defines goals in a way that like leaves no leeway for like stuff to break internally. And like this at best gets you like a few bits of information about where the goal is, which is like pretty good in a vacuum, but you really, really want something that's like much more robust, like actually identifying the goal. Because like in the real world, there will be like optimization pressure applied like in a number of ways, even if you aren't plugging it directly into loss functions. Like that's part of the reason why we need like a lot more properties and like a lot more like conceptual work done into like figuring out what objectives actually, like how to actually extract these objectives. Yeah.
Cool. Maybe Johannes? Oh, well, one sec.
Yeah, I was just wondering, do you have to like make a list of possible goals and then check against each one of them, or do you imagine like automatically like possible misaligned goals?
Yeah, do you want to take this one?
Yeah. So like that's a good question. Like this is something that we're definitely working with a more constrained case here. In that, like in this case, we're working the like something where we can just list out like all the abstractions in the environment and think like, okay, these are candidate like targets that the model could be like model's cognition could be pointing toward. And yeah, the more we thought about it, just like the problem as a whole has like way too many different variables to figure out in terms of like A, figuring out how to extract the structure, B, figuring out like what structures, what like abstractions those point to within the environment, how to like interpret, translate between those two structures, all of that kind of stuff. So like, yeah, for the purposes of like our first set of experiments to like just get insights about whether or not this property is a good one to rely on, we figured we'd go the constraint setting where like we don't have to worry about the other problems. We try to work in an environment where we like already know what like the target abstractions could be, and we just want to figure out like, okay, is there a way to like extract the structures that are related to them? So like, yeah, the stronger versions that actually apply in the real world would need to like also solve the problem, like figuring out which abstractions those like translate into. But like, yeah, we have some ideas for that kind of stuff, and that's like Paul had like a large segment on that in terms of like auditing games in this thing that like we removed mainly because it was like pretty involved to get into in terms of the entire thing. But yeah, that's definitely something we're thinking about. We definitely have some thoughts. I'm guessing Paul has some ideas here too. Yeah.
Yeah. So this is related to this point about abstraction detector for sensory inputs. So theoretically, it might be possible that given any particular sensory input stream that the AI has during like training or like up until this particular point, you can take that as a data set, and maybe there's some method that you can use to extract all the set of all possible abstractions that the AI must use. And I think this is sort of what John Wentworth is working on at the moment, like with his pragmascope thing. Yeah, and so like theoretically, yeah, if you had like loads of compute, you could like do this, and then you could be tracking like potentially all abstractions that the AI could possibly be using, and that might allow you to refine things rather than having like predetermined notions of what goals the AI is going for. But yeah, hopefully we don't need to do that kind of level of computation. Maybe we can use like prior knowledge about the training setup environment to kind of narrow things down into like, you know, yeah, more likely abstractions or more likely goals that they might be aiming for.
Yeah, another thing is that like while John's work, like if John like solves all of the abstraction stuff that he's working on, that would definitely like solve this problem wholesale for us. But I think that like the specific way we were approaching this in terms of like figuring out the goal extraction part first gives us like a lot of bits into solving that problem in the more like integrated setup here. Like there's definitely at least one version of events I can see playing out where we don't need to solve that problem at all, where we can just like extract a goal structure and then let some kind of like optimization procedure figure out what to do with that in terms of like steering it the right way. But that's like really, really ambitious. And in terms of more realistic setups, I still think that's like once we solve all of these problems, I foresee like figuring out how to integrate like abstraction detectors feels like it feels like an easier case than solving it in the fully independent sense. So yeah, that's part of the reason why we're approaching this in an integrated way, because like we expect those problems to also become easier once they're part of the setup. Yeah.
Yeah, and also it might be useful even if we can't. Suppose we identify this goal structure and we see it's related to these set of this 5 abstractions, and we can't actually interpret what those abstractions are. That might be useful because then we can like say, okay, this AI is optimizing for something, but we have no idea what it is, so we're going to shut it down and like retrain them. Like maybe we could limit ourselves to regimes where we have optimizers, but they only optimize for things that are within the realm of like human abstraction. So that might be.
Oh yeah, and to the extent that like to the extent that there is a version of this problem that we have to solve regardless of like how optimized we can get our setup to be, that feels like it's something that you have to solve it in terms of any alignment agenda. That's like feels like an unavoidable problem regardless. Like at best, this thing can like remove a lot of the frills involved and just get like the bare minimum version that like absolutely needs to be solved to like for all of it to work. But like yeah, there definitely still needs to be like some component of like ontology translation that works. The hope is that this version will just like minimize the problem as much as like make the problem as simple as possible, because like bunch of surrounding stuff. Yeah.
Yep. Cool. Did you have a question?
Right. So as far as I can tell, the high level goal here is to derive a set of robust methods to find goal structures in neural networks, and right, sure. So the thing here is I'm still a bit I still have some vagueness around whether you are relying on say John Wentworth solving ontology identification for solving the hard alignment problems as written on this in the slide, or yeah, that's basically the thing that just is in my head right now.
Well, okay, so like I was saying, even if ontology identification isn't solved, whatever that really means, a way of like translating from an AI's ontology to our ontology, then at the very least we can identify that it's optimizing for something, but not necessarily something, so we know it's optimizing something and we know that we can't interpret that. So that might be useful as one point.
Yeah, another point is that like I see like John's work as being much more general in this regard, that like if John solves like everything he's working on in terms of abstractions, that like is much more powerful than the version we would need to like solve the problems we run into with this version of things. When I last time I spoke to him about it, his main take was that like his version of abstractions is like powerful and like simple enough to the extent that like he anticipates the main problem we'll run into is that objectives are just too complicated and that abstractions is simpler to work with as a starting point. But yeah, I think that if you start out with objectives and it actually works, like you can actually extract these things to begin with. I think that the problem of like translating between the things that these structures represent and like human understandable abstractions becomes like much more reduced than the fully general problem of like figuring out abstractions. Like there are like many like minor reasons we think this is the case. Like for example, one thing is that like I mentioned before, we're working with a constrained case here where we don't have to worry about like what the abstraction set might be, and we just have to figure out how to extract the goal structure while knowing what the abstraction set is. So one reason why figuring out like abstraction or translation in this specific case might be simpler is that you can work with like similarly constrained setups in the like when you get to that step, because you've already solved so much of it so far, and there's like a structure that you vaguely know the shape of and like the conceptual structure of, so you can like rely on some of that in terms of like guiding your intuitions around. So you basically aren't like trying to figure out the general, no context, independent problem. You're like working with a constrained version of it for a specific kind of like setup that like, yeah, these feel like abstract, ambiguous arguments. But like there are like many minor reasons that like form the way we think about this. This is actually in one of the docs, I think, that Paul Revere wrote about, like in terms of why we think that we don't actually require John solving abstractions to be step 4 of how we solve a line. But like there definitely are like many reasons why we think it would be easier in this case, is the big picture thing.
Yeah.
Could you elaborate a little bit on why you think current systems are as having goals as being a pile of heuristics?
Yeah, I personally don't think they're they're probably better modeled as like a pile of heuristics, but I think yeah, so that's the first comment. And I guess it's just kind of surprising that it does work. Well, maybe it's not. No, it's probably not surprising, but I think maybe at the level of abstraction of like the May solving model and like agents and the level of like generality of this particular method, it's enough that it can apply for both systems. But yeah, I think obviously we do need to maybe wait for more dangerous systems to arrive before we can get like more bits of empirical evidence. Yeah.
Yeah, one thing is that like I think that I suppose like property number 1 of any kind of interpretability tool we devise for goal detection is that it has to work for some systems and not for other systems. Like it has to work properly for some systems and not for other systems. There are definitely many systems that don't have like the notion of objective that we define like yeah, up here, like in terms of like general purpose cognition circuits somewhere in the model that are like built to deal with like diverse, rich, complex tasks and environments. Like there definitely are many models today that don't have to deal with that kind of stuff, and so don't have like this notion of goal. We really like our tools like should not like say, okay, this is like what this model's goal is in terms of like some kind of best guess form from like some kind of composite look at the heuristics. Like you want the tools to just ideally like not really work as well on those kind of things. And like yeah, the idea here is that like any kind of powerful transformative system will likely be like trained on like a very complex environment or a complex kind of task that will require like general purpose circuits. Like I guess like we are making the very preposterous claim here that powerful AI will require some kind of like general purpose internal cognition machinery, like whether you call that like search or meso optimizers or whatever. Yeah, we'll probably have to require that to be like really transformative.
Yeah. So part of what's annoying about working on this stuff is that, yeah, you've got all these different potential, yeah, you don't even really know what an agent is. We're trying to figure out like which notions of goals applied to which notions of agents and stuff like that. But we're doing our best.
Yeah, that's part of the reason we started out with like the maze environment, because that seemed like the best, simplest case we could get for like a policy that like plausibly has general purpose circuitry in there, because like a complex maze environment that like seems like the simplest possible version you can there learn there'd be some kind of like internal search.
Yep. Cool.
Yeah, so there's an edge case here, which seems like not totally impossible to me, which is meiotic goals, which are like goals to find or discover like some object level goal to pursue. So these are like plausibly goals that humans have, like try to like decide on a passion and then pursue it or something like that. And it seems possible that like AIs will have goals like this, maybe if they're either yeah, human-like, human simulators, or if they're maybe trained on a range of diverse tasks or something like that. So I'm curious if your setup is like posed to be able to detect goals like this. I think there's like maybe an easy mode where you're like optimizing hard for deciding on an object level goal to pursue, and then there's like a hard mode where like the kind of optimization doesn't really kick into gear until an object level goal is determined.
Yeah, I guess I'll quickly say that my first take is that I think, yeah, I'm not sure if this will be able to detect, or what was the terminology used? Meiotic. Okay, cool. I don't think it will be able to detect meiotic goals or values or whatever, but I think insofar as in order to pursue those meiotic goals, you'll need to have like instrumental goals, and those involve like taking actions in the world that we're concerned about. Then I think this will be able to pick up on those, and so that might be somewhat useful. But it depends on, again, like what structure these meiotic goals take. So yeah, Arun, do you want to add to that?
Yeah, I mean, in terms of, I feel like even if you feel like running that kind of like did you say meiotic or myopic?
So it's
I can't. Paul, could you just? Yeah.
it's spelled MAIEUTIC.
Okay,
I'm not sure if I'm
okay,
pronouncing it right or not.
Okay, I'm just going to treat that word like in the context of conversations. That's not something I've heard before. But yeah, and it feels like if you, with like the thing you're really worried about, like a model doing, is applying like a lot of optimization path, like funnels towards some kind of outcome here. So it feels like to the extent that that kind of like meiotic goal searching procedure doesn't have a lot of optimization power applied to it, we aren't that worried about it, because the second you do start to apply optimization power towards some kind of like goal that you can discover with that, then you started the tools. And like if you do apply a lot of optimization power in your like meiotic goal selection thing, then you do detect it without things. So like it feels like the dangerous part comes in once the model starts to like seriously apply optimization power to like select for some kind of outcome or like action or something. And at that moment, like our tools like will start to like apply in terms of like detecting what the goals are.
One sec.
Yeah, so I think the danger depends on like how good the agent is at optimizing for an object level goal once it has it. So I think the issue is like if you're not able to detect meiotic goals during like training or something, then there like might be an instant where like suddenly like some object level goal is determined and the AI starts pursuing it very hard. And if the AI is like sufficiently capable, then maybe we're all dead because like it events nanobots or something like that. So it seems like in this case we need to rely on like the time of like us being able to shut the AI down once we detect this object level goal, which like might be the case for like most scenarios. But if it was necessary to like detect that the AI is going to be dangerous during training or something like that, then this might be a failure story.
Yeah,
So,
I personally haven't thought about this thing enough to like give a good answer to that. But yeah, Aaron, do you wanna?
I haven't either, but this seems like somewhat isomorphic to just like the base optimizer selecting for like goals you don't like in a way that like because you. I suppose the thing is, my take here is that like, what's the actual process of like goal formation here? Like, in terms when you run your meiotic goal search procedure or whatever, in terms of searching for an object level goal, at some point like you start to form like whatever that object level goal is, and the second you have that like representation, then you have like a goal internally that like is very strongly at odds with whatever your like overseer loss function would return, and at that point you'd start optimizing away from that. So it feels like even in this kind of scenario, the second you like have something internally that is that is like that can be described as a goal in any sense, like it starts to like optimize away from that. Like it doesn't feel like you just have to apply like any kind of manual oversight. I guess I'm thinking like when you have like that kind of integrated oversight function, what is the trajectory by which like things start to go bad? Like how does it evade that kind of like optimization, I suppose?
Okay. Cool. Cool. Yeah, Jeremy. One sec.
What property can you use to distinguish between like a deceptive goal and the actual goal?
Between a what goal and an actual goal?
A deceptive goal and an actual goal. Yeah, do you want to start?
Wait, could you elaborate on what you see as being the difference there? Like, what do you mean by deceptive goal? Like, the goal that the model has, like, then it's pretending to have?
Yeah, the goal that the model wants you to think it has, or expects you to reward it for.
Yeah.
But like, in distribution, during training, but not after.
Yeah, I mean, I suppose this relies on like mechanistic structure, right? Like if you have the model if like there is like some kind of like information contained within the internals of the model that corresponds to like some underlying notion of goal that exists, like our distribution or whatever, that information still has to be present inside the internals of the system. And so like if you come up with a general notion of goal that like fully like actually describes like the model's like objective in a general sense, then like it feels like that would be covered here in terms of like you would extract all of the information relating to the model's actual goal in any given context. So like deceptive goals simply wouldn't like be strong in like unless you like run maybe if you run like really hard optimization against it, maybe, but like by default I expect that like any kind of like actual goal you have, a deceptive goal you have, wouldn't like hold up to the kind of internal structure you would expect a goal to have, I suppose. Like I don't know, that's those a lot of words. I'm not sure whether like that answers your question.
I can. There was a shrug from Jeremy.
I suppose like
yeah,
my answer very in short would just be like internal structures of the like if you, even if you're deceptive, you'd have to like actively encrypt your internals to beat like a mechanistic overseer. And like at that point you probably already lost. Like the point of putting stuff into a loss function is that you never entered deceptive space in the first place. Like suppose that's like argument number one. I can think of like other arguments for why even if you do, this might work, but like the first one still seems like the strongest to me. The other ones seem mostly shaky. Like this point of putting in a loss function to prevent it from entering like the space where it's like deceptive enough to encrypt its internals in the first place.
yeah. Okay, I guess I'll add to that is that maybe there's this like more theoretical answer, which is like if you have a deceptive goal, it has like a deceptive goal structure, and so we can detect it, and so we're happy because we're like monitoring the system like all the way through training, and so as soon as it has a deceptive goal, it has to have a goal structure associated with that deceptive goal, and therefore we can detect it. That's like, I don't really buy this too much, but it's like a theoretical argument.
I suppose like if you have like an actual goal somewhere and you have another goal that you're pretending to have, this tool would ideally like just recognize the first, because you're like searching for the thing that actually is the model's goal by whatever like functional property you define the goal to have.
Functional property. What's the functional property that differentiates these things? It's
Wait, is someone speaking away from the mic?
Yeah, that was me. So, I'll say that necessarily is a functional difference between them, but so it's just like maybe there is, and if we could find this like additional property, then we could differentiate between them. But if there isn't, then okay, we've just detected it's a goal, and we see that it's optimizing for this thing. We see maybe there's another goal or something like that, and it's optimizing for that thing, and we have some information there. But I guess another way that I'm seeing it is that suppose like we don't detect the deception like emerging during training, then if we're continuously monitoring like during deployment, okay, this is like okay, maybe this is like really dangerous. Stop speaking, but anyway, so suppose it is deceptive during training, we don't detect it, and so we're like monitoring its goal, and it seems to be like good, and it's not able to like obscure its. Okay, I think we're already in dangerous territory. But I was just going to say that, okay, then as soon as it switches its goal to like actually pursuing the deceptive thing, like, trying to, overtake the overseer or like remove the off switch, then we would see that as its goal and we could intervene at that point. But I agree, we would want to deceptive doing it post-op.
I guess my take is like if the goal exists anywhere in the model in the first place to have like the notion to have like the intent to like defect at some point, then insofar as there is like some information theoretic way to like notice that mechanistically, then if you have like a robust notion of a goal, then that should be what it detects. Like I can't off the top of my head, like I can't think of like the property you could use to separate those two. If we had, we'd have solved deceptive alignment already and we'd be giving a very different presentation. But like the idea here is that like those properties are like something you can discover in terms of like if you keep trying to discover like understand like goal structures better and like come up with like convergent notion of okay, this is the objective of any given system within like a broad class of things, then that should only hold for like the actual goal of the model, not for like any slightly any like behavioral things that the model does in terms of like this is what the model chooses to do after doing the internal computation of do I defect now or not, or like any kind of like difference from what its actual goal is. if that, as long insofar as there is a way to detect like the actual goal in any theoretical sense, it feels like the proper goal detection method should do it. I can't think of what that property might be, because that's like a really powerful property to find, but I think it exists, and like there's no reason to think it doesn't exist, because like there literally is an information theoretic difference there.
Okay, I guess I'm just going to stick to the answer, which is like the theoretical one, where like deceptive goals are still goals, and we can detect them. Well, if we can detect them, then we can.
Yeah.
Cool. Any other questions? Okay. Maybe. What time is it? Okay, 17 past. Like maybe some people want to go, and they're just like feeling a bit awkward sitting here. So like we can talk after. Like yeah, we can continue the Q&A afterwards. Cool. All right. Thank you, guys. People are clapping for you. Don't worry.
I heard some of that through the mic. Yeah. You said continue the Q&A afterward.
I was just saying, like, we could continue it now. Like, is there a problem if we, like, just maybe... Okay, yeah, okay. Maybe we'll just, like, go with, like, one last question or something.
Sure. So just to wrap up that, like, meiotic goal convo. So I think the challenge is, like, if you're able to discover, like, the kind of structures that are associated with goals, even in the case where the goal is not actively guiding the model's behavior yet, then you're good. And I can imagine that some like possible elaborations of this agenda will like achieve that, and like some might not. So as long as you're kind of achieving this hard mode version, it should be okay.
Yeah, this is Paul. Do you have an answer? Like,
Yeah, I was gonna. Yeah, that sounds good. I guess for the time being, I'm putting a lot of like my hope on. Okay, even if it does have a meiotic goal and we can't detect it, but it has like instrumental goals and we can detect those, then we might be good. I don't know how, because that just seems like an easier ask, and I kind of feel like that can get us far enough in stopping dangerous behavior, but I'm willing to be challenged on that. But yeah, I agree. Like it would be cool to have like this more robust thing.
Sure. I guess like one challenge with that is like at least using the human case as a benchmark. Like agents might not be too goal directed before they find the object. So you could might like some person who kind of wants to have a hobby or a passion or something like that, like isn't really consequentialist about this. Like once they decide on a goal, I'm going to be the best airplane pilot there is, or something like this. Then they pursue hard. Yeah, sure. But so I think the issue is like during training, you have a model that arises that like kind of is supposed to optimize really as it settles on an object level goal, but isn't optimizing hard at all before that. And then if it's sufficiently capable, then like once it settles on an object goal, you're like going to like create nanobots and take over the world.
Paul, Mike.
Yeah, it like depends on how good the deployment, like how long it takes, like detect you like shutting down or something like that. Yeah.
Sorry, I didn't get to say I don't think you heard my points.
I did not. Yeah.
Okay, well, doesn't matter. I was just like maybe slightly pushing back on that, and I guess I think the conclusion was like, but you could run into a situation where it has meiotic goals during training, you can't detect them, you detect the instrumental dangerous goal during deployment, but because it's already got this like massive capabilities during training, it like, you know, creates nanobots before you can shut it down or something like that.
Yeah. I mean, my take is that like this would have to happen like in one forward pass at that point, because like this is like happening during training. So like if your model was like suddenly like applying optimization power, and like you want to detect that, you want to like prevent that from happening, it would have to achieve all of that within like one forward pass of the model, because that's the point at which like your overseers like starts to apply like overseery things. So like insofar as like you need the model during training to like suddenly decide on a goal and then start like optimizing on it really, really hard and like make nanobots or whatever. Like you need that to happen within one. You need all of that change and all of its like dangerous stuff to happen within one forward pass before like optimization starts pushing it away from that. And in the first place, I think there's like other theoretical arguments you can make about how like the presence of the overseer at all pushes the model, doesn't like push the model into the kind of space where like this kind of behavior would immediately erupt, like in terms of like what kind of models in parameter space are likely to like suddenly shift to this kind of behavior. I think the presence of the overseer might push you into safer territory, but I think the other argument is stronger in that like the overseer being present and like monitoring you at every single step means that like you'd have to have all of that shift and everything happen in one turn. Actually, I think there's like a comment from Paul at some point in some post somewhere echoing a similar point. So I'm just not Paul Cristiano. So I just want to find that comment.
Yeah, maybe, sorry, to summarize your point, was it like if you can do sufficiently good monitoring, or like, you know, each forward pass, then like, yeah, then you're good, maybe.
Yeah, and basically like if you're putting it into a loss function, then yeah.
But then, yeah, I guess, and then that's just like a question of like how good the method is and like how computationally, you know, demanding it is to run this method like at every single forward pass and so on, but yeah.
Oh, I meant like putting it into the loss function, not like overseer at every, yeah.
Okay, yeah, okay.
Yeah, hold up, I'm just finding this, okay, yeah.
Yeah, wait, so I might have missed something. What are we putting into the loss function exactly?
The oversight mechanism, like, wait, who's speaking?
This is James.
Okay,
yeah.
That's one of the same question. Yeah. So it's like you put the oversight from a mechanism into like into the loss function. Basically, some kind of like oversight signal that says like figures understands the goal and like says whether or not like the human overseer would like it. Even if you're not, obviously you'd want this to be auto. Like I don't know how familiar are with imitative amplification, but it's basically like about amplifying the human like feedback signal on some kind of like some kind of channel. So like if you can figure out like if you can understand the mechanistic notion of a goal in a system, then you can like feed that into like imitative amplification in terms of like a scalable signal of whether or not a human would like the actual objective of the system, and then plug that into your loss function as a signal to the system. Yeah. I think this is the comment, by the way. Like I'm just going to put it into the main thing. I did not read it through, but I think this is the one where it's put in. Okay, yeah, it is this one, and it's like in the second half of it's toward the end of the comment. Search for the paragraph that starts with our goal is to learn a reporter. Yeah. A goal is to learn a reporter that describes the latent node of the model and to keep this up to date as the model changes under SGD. If thinking about SGD, you usually think concretely about a single step of SGD and how you could find a good reporter at the end of gradient descent step, assuming you had one at the beginning. So like, he goes into it in more detail here, basically responded to Nate's criticism. Like if you start to undergo like a sharp left turn, the elk head breaks, whereas that like Paul's response is basically like, but you are still dealing with like an SGD type system. So like all of the changes have to happen in like one step such that the elk head can't keep up. And like that's a much harder ask in terms of like how strong your shift has to be.
Okay, nice. I'm not sure if I follow fully, but I will stare at this comment a little bit later. And yeah, also just kudos on this agenda. I think it seems like, yeah, it feels more hopeful than like most other stuff.
I mean, to be fair, I still think we're all, like there's a very good chance we all fail, but I still think this has a lower chance to fail than most other things.
Yeah. Yeah. Cool. Okay. Thanks.
Oh yeah, thanks for listening. Are you part of Maths 4.0, by the way?
Oh, yeah. So I'm a math scholar right now. I'm in the multipolar stream.
Okay, that makes sense. Yeah.
Cool. Yeah, everyone else left. That was a pretty good turnout. I think like 20 people or something. Maybe there's around 20 people.
That is way more than I expected.
Yeah,
I expected like 4 or 5 people.
Yeah. So yeah, cool. All right. Yeah, good job. That was a great talk,
Yeah.
great first half. Like, I was pretty impressed, wasn't
Yes.
it?
Likewise, yes.
Okay. Yeah, cool. I guess I'll speak to you soon.
Yeah,
Okay.
cool. If you get
Cheers.
the recording for this
Thanks for the
somehow
talk,
before
guys.
I do, send that to me.
Wait, sorry, Joe?
I was just saying thanks for the talk.
Oh, cool. Thanks for attending.
I might
If you
have,
have a
comments
question
later.
Okay, cool. Yeah, just hit me up if you do. I noticed you unmuted yourself a while ago, and I was like wondering whether you had a question, but other people are still asking, and I completely forgot.
I was considering asking something, but it was kind of I can send you comments about
Okay,
stuff.
cool.
It's fine. I don't think it's anything you wouldn't have thought of anyway. So yeah, I'll
I mean,
send some stuff.
that most likely is stuff we haven't thought of. We've only been working on this for like 6 months.
Well, yeah, we'll see. We'll see. Anyway, yeah. Cheers for the talk. Bye for now.
Cool.
Thanks
See
for
ya.
showing up,
Thank you.
Yeah, and Paul, yeah, if you get the recording for this thing before before I do somehow before it's like posted on the Slack or something, send that to me.
Okay, yeah, we'll do. Awesome.
Cool.
All right. See ya.
Yeah.
Oh, yeah.